Welcome to another lecture in the course on 3G and 4G wireless mobile communication systems. Just a brief recap of what we did in the last lecture. In the last lecture, we completed our discussion of the previous module, and we said we completed a list of some topics in the previous module. These topics included describing or characterizing the wireless channel, namely with parameters such as RMS delay spread, the coherence bandwidth BC of the channel, ISI or the intersymbol interference, flat versus frequency selective fading wireless channels, the Doppler shift of a wireless channel which results in a time varying wireless channel. Remember, we said that mobility or the Doppler shift results in a time varying wireless channel. We also looked at the concept of a coherence time, or the time for which a wireless channel is approximately constant, the Doppler spectrum and the Doppler spread, and the concept of underspread channels. Hence, we have looked at several aspects to comprehensively characterize the behavior of the wireless channel. Please revise these concepts again to enhance your understanding of the wireless channel. We also started our discussion on the next module, which is another important aspect, or which is a very important technology in third generation wireless communication systems, namely CDMA, or code division for multiple access. This is what we are going to discuss in this lecture and the coming subsequent lectures, some subsequent lectures. And we also said CDMA, as by definition, in fact, as the name suggests, code division for multiple access, CDMA is a multiple access technology. All right, and this is the point at which we stopped in our last lecture. So, let us continue with our lecture today, that is, let us develop this concept of CDMA further. So, let us start formally our discussion on CDMA, which is a multiple access technology. Now, what do we mean by multiple access? Let me consider here a mobile communication scenario. I am considering a base station which is transmitting to two users, that is user 0 and user 1. So, I have a base station, this is a base station that is transmitting to two users, that is user 0 and user 1. Now, remember, there is a single wireless channel, that is the air interface. There is no, unlike a digital communication or a wire line channel, there are no separate channels for user 0 and user 1, but the channel for user 0 and user 1 is the same medium, that is the wireless air interface. Hence, there has to be a way of transmitting independent information to each of these users separately. So, what do we want is, we want each of these two users, that is user 0 and user 1, to access the base station, or in other words, what we want is multiple access. Because the channel here is the common air interface, this is the common air or vacuum channel, this is the common wireless channel. Both the signals that are being transmitted by user 0 and user 1 are interfering at the base station if they are transmitted directly. Hence, we need a way for accessing independent information over this common channel independently by user 0 and user 1. In other words, we need what is known as multiple access. Hence, CDMA is one such technique that enables multiple access, and this stands for code division for multiple access. Hence, the name code division for multiple access. Let us look at some other simple wireless technologies. If you had taken a basic course on wireless mobile communication, you would have seen that TDMA is another multiple access technology. In fact, TDMA stands for time division for multiple access, in which if I have time, I will designate some time slot for user 0 and I will designate some other time slot for user 1. Hence, I am transmitting to user 0 and user 1 at different times. This is time for user 0, this is the time for user 1. Hence, I am transmitting signals to user 0 and user 1 at different times. Hence, I am dividing the signals of user 0 and user 1 in time. Hence, this is known as time division for multiple access. That is how I am transmitting independent information signals to different users. Another technology which is even before TDMA is what is known as FDMA, or this also stands for frequency division for multiple access, in which instead of dividing signals in time, what I am doing is I am allocating separate frequency bands for user 0, another frequency band for user 1. So, I am allocating band 0 for user 0, I am allocating band 1 for user 1. So, I am distinguishing both these users on the basis of their frequency bands, that is user 0 has to tune into his band 0 to get his signal, user 1 has to tune into his band 1 to receive his signal. Hence, I am distinguishing different users on the basis of frequency. This is known as frequency division for multiple access. Remember, my aim is multiple access, that is somehow I want to transmit signals to these different users over the common air channel. There are different ways to do it. First one is one way is through time division for multiple access, and you should be familiar that TDMA is used in GSM technology, which is the basis for all the second generation mobile phones. FDMA or frequency division, in which the signals are transmitted in two different frequency bands, is another way of doing it. You should also be familiar that this, maybe some of you are familiar that this is a first generation mobile. In fact, the very first technology that was used in cellular networks or cell phones, or the first generation cellular technology, was based on frequency division for multiple access. However, as cell phones and cell phone technologies became more advanced, people progressed onto more sophisticated multiple access technology such as CDMA, which stands for code division for multiple access. Now, why is this a superior technology? We are going to see the reason for CDMA being a superior technology as we go through this lecture and the next couple of lectures, but CDMA is essentially a multiple access technology, and as you will realize, a multiple access technology is at the heart of every cellular technology, because every cellular technology implies that this common air channel has to be used to transmit multiple information signals to different users. Hence, I need a multiple access technology. There are several multiple access technology. CDMA is a more sophisticated multiple access technology. So, let us start our discussion of CDMA. As I said, I want to transmit to two users, that is 0 and 1. Let us say I am transmitting the symbol A0 to user 0 and I am transmitting A1 to user 1. All right, let us say I want to transmit the symbol A0 to user 0 and I want to transmit A1 to user 1. Now, instead of transmitting these directly, what I will do here is I will multiply these with what are known as codes. Remember, code division, CDMA stands for code division for multiple access. So, there are codes involved in this multiple access scheme, and those codes are nothing but the sequences that I am going to show you here. Let me write one such code. Let us say for user 0, I use the code which comprises of 1, 1, 1, 1. This is a code of length 4 symbols and each of them is 1. That is why I have a code which is 1, 1, 1, 1. let me call this code as code 0, and for user 1 I will use a different code which is 1 comma minus 1 comma minus 1 comma 1. I will call this code as C1. So, what I am saying, for each user I have a different code. For user 0 I am using the code 1 comma 1 comma 1 comma 1. For user 1 I am using the code 1 comma minus 1 comma minus 1 comma 1. Now, to transmit the signal, what I will do is I will take A0, multiply it by its code. So, I will take A0, multiply it by the code 1 comma 1 comma 1 comma 1, that will give me the sequence A0 comma A0 comma A0 comma A0. This corresponds to user 0 after multiplying by the code. So, I am taking the symbol of user 0 which is A0, multiplying it by its code C0, that gives me A0 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 A0. Similarly, for user 1 I will take the symbol A1 and I will multiply it by its code which is 1 comma minus 1 comma minus 1 comma 1. So, after multiplying with the code I will get A1, A1 into minus 1 is minus A1 comma minus A1 comma A1. So, after multiplying user 1's symbol with his code I get A1 minus A1 minus A1 comma A1. Now, what I will do is I will add the signals corresponding to these two signals corresponding to user 0 and user 1. So, I will get A0 plus A1, A0 minus A1, that is A0 minus A1. Again I will get A0 minus A1 and I will get finally I will get A0 plus A1. So, this is what is the net signal that is transmitted over the air. Okay. I am taking the symbol corresponding to user 0, I am multiplying it with its code. I am taking the symbol A1 corresponding to the user 1 and multiplying it with its code which is different compared to the code of user 0. Please notice that this user 0 code is 1 comma 1 comma 1 comma 1, user 1 code is 1 comma minus 1 comma minus 1 comma 1. User 0 after multiplication with the code gives me this sequence A0 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 A0. User 1 after multiplication with the code gives me A1 minus A1 minus A1 A1. I am adding both these sequences, that gives me A0 plus A1. The second symbol is A0 minus A1, the third one is A0 minus A1 and the fourth one is A0 plus A1. Okay. So, finally, let me write that down again. What is transmitted is A0 plus A1, A0 minus A1, A0 minus A1, A0 plus A1. This is what is transmitted, this is what is, this is the transmitted signal. So, I am taking those symbols corresponding information symbols corresponding to the two users 0 and 1, I am multiplying them with their spreading codes, I am adding these multiplied signals, combining them, adding or combining them, and then I am transmitting them over there. So, what I am transmitting over there is just one single signal. Remember, the whole air channel is simply one channel. I can transmit one signal over that channel. I am transmitting this combined signal. Now, at the receiver, obviously user 0 has to extract his own symbol which is A0, user 1 has to extract his symbol which is A1. So, at the receiver, what I am going to do at the receiver at user 0, I am going to again multiply this by the spreading sequence of user 0. So, I am going to multiply this by 1 comma 1, comma 1, comma 1, and I am going to add everything up. So, I am going to take this signal that is transmitted over the air at user 0. So, let me mention that clearly, this is at user 0. I am going to multiply with the code of user 0, that is C0. So, I am taking the code of user 0, which is 1, 1, 1, 1, multiplying this signal with 1, 1, 1, 1, adding them up. Let us see what we get. A0 A1 into 1 gives me A0 plus A1 plus A0 minus A1 into 1, that gives me A0 minus A1 plus A0 minus A1 into 1, that gives me A0 minus A1 plus A0 plus A1 into 1 gives me A0 plus A1. Now, when I add all of these, you can clearly see I get A0 plus A0 plus A0 plus A0, which is 4 A0 plus A1 minus A1, which is 0, minus A1 plus A1, which is 0. So, corresponding the interference corresponding to the symbol A1. Look at this, in this signal that is transmitted over the air, which is A0 plus A1, A0 minus A1, A0 minus A1, A0 plus A1, there is interference corresponding to the symbol of user 1. However, after I multiply with the spreading sequence corresponding to user 0, this interference is magically removed and I only get something that corresponds to user 0. This is 4 times A0. I can divide by 4 and get back A0. So, this is simply A0 scaled by 4. The scaling does not really matter, so do not pay attention to that. But in essence, what I am getting back is the signal corresponding to user 0 and the interference corresponding to user 1 has been completely removed. This, and now let me illustrate what can be done at user 1. Let me take the same signal that is transmitted over the air. Remember there is only one channel, so you can transmit only one signal, that is the key. I cannot transmit two independent signals for A0 and A1, that is at the same time and in the same frequency band. I am taking the same signal, that is A0 plus A1, A0 minus A1, A0 minus A1, A0 plus A1. Now, at user 1, I will multiply it with his code C1, which is 1 comma minus 1 comma minus 1 comma 1. Now, let me multiply it with the code of user 1 and let me add it up and let us see what we get. A0 plus A1 times 1, that gives A0 plus A1 plus A0 minus A1 into minus 1, that gives me A1 minus A0 plus A0 minus A1 into minus 1, that gives me A1 minus A0 plus A0 plus A1 into 1, that gives me A0 plus A1. Now, when I add all these things together, I will get A1 plus A1 plus A1 plus A1, which is nothing but 4 A1 plus A0 minus A0, which is 0, minus A0 plus 0, A0, which is 0. Hence, the interference corresponding to user 0 is 0. Alright. So, at user 0, I am correlating, I am multiplying with the code corresponding to user 0. Look at this, this operation multiplication is also known as correlation. This multiplication operation is also known as correlation. Hence, at user 0, I am correlating with his code, which is C0, I am able to recover the symbol A0. At user 1, I am correlating with his code, which is C1, and I am able to recover his symbol A1. So, by correlating with the different codes corresponding to the different users, I am able to recover the signal both of user 0 and of user 1. Hence, over the common channel at the same time, remember these signals are being transmitted at the same time and in the same frequency band. So, I am using the same time, not different time, and I am using the same frequency. However, by intelligently using different codes, I am able to recover the signals of user 0 and user 1. In other words, I am able to multiple access the information signals of user 0 and user 1s. Hence, the name CDMA. CDMA is CD plus MA, which is I am using code division. I am dividing information on the basis of codes, and thus I am achieving multiple access. I am using codes to achieve multiple access. I am dividing information signals on the basis of codes. I am resolving the signals out of the common signal on the basis of codes. Hence, the name code division for multiple access. That is why CDMA has its name of code division for multiple access, which is I am using codes for multiple access. Hence, code division for multiple access. As I said, this is the key for every third generation wireless technology name. If you talk about HSDPA, if you talk about UMTS, you might talk about CDMA 2000, 1x EVDO, even the second generation technology of IS95, that is the original CDMA to second generation CDMA folds, all of these are based on CDMA, which is the physical layer multiple access technology. And as we have seen already, the key operations here are first multiplying with code. So, the key operations in CDMA are first multiplying with code, 2 combining signals of all users, and 3 at each user, that is at each receiver, I correlate with the code corresponding to that user to recover the symbol corresponding to that user. Hence, the third step at the receiver is correlating with, that is correlating with the code to recover the signal corresponding signal or symbol corresponding to that user. So, these are the 3 steps of CDMA, that is multiplying with the code, combining the signals of all the users, and then correlating with the code at the receiver to recover the signals of these users. Now, let us look a little bit more at these codes. I have not said about these codes because it seems like magic. I mean, what we have done is seems like magic, because we have transmitted both the signals on the same interface, yet we are able to recover the codes at the receiver. Why is this happening? For that, we have to look at the codes themselves. It looked like I have not talked about how I have come up with these codes, because I have just showed that we are employing these codes, but I did not explain a reason for why such codes should be employed. Let us look at why such codes should be employed. So, I take this code C0, which is 1, 1, 1, 1, and I take code C1, which I said is 1, minus 1, minus 1, 1. Now, let me correlate C0 with C1, that is I will multiply C0 with C1 and then I will add. So, when I multiply 1 with 1, I get 1 plus 1 into minus 1 is minus 1 plus 1 into minus 1 is minus 1 plus 1 into 1 is 1. When I add these up, it gives me 1 minus 1, which is 0, minus 1 plus 1, which is 0, hence the net is 0. This is what causes the magic to happen. Remember, if two vectors have dot product 0, we have a name for that, we call those vectors orthogonal. That is the property these codes are exhibiting. These codes are in fact orthogonal. These codes are in fact orthogonal. That is the reason you are able to recover the symbols corresponding to these. Why are you able to recover the symbols corresponding to these codes? Because the code employed for user 0 is orthogonal to the code employed by user 1. Hence, when you are correlating with code 0 at user 0, it is orthogonal to code 1. Hence, that interference component is going away to 0 and you are able to recover symbol corresponding to user 0. Similarly, at user 1, when you are correlating with C1, that is orthogonal to C0. Hence, that interference corresponding to user 0 will become 0 and you are able to recover the symbol corresponding to user 1. Hence, this orthogonality of codes is key to CDMA. That is, we want to employ codes which are orthogonal to each other, so that we can recover the signals corresponding to each user. Alright. Now, these codes have a name. I have called them codes so far. They have a more specific name. These codes are known as, or such codes are known as spreading such codes are known as spreading codes. Now, why the name spreading codes? To understand that, we have to look at this system a little bit deeper. Let me start with the symbols transmitted to user 0. Let us say I am transmitting symbols A0, different symbols to user 0. Let us say I am transmitting symbols at 1 kilobits per second. Let us say I have a digital communication system which is transmitting symbols at the rate of 1 kilobit per second. Then we know that the time per symbol, equals 1 over 1 kilobit per second equals 1 millisecond. Alright. So, I am transmitting symbols at the rate of 1 kilobits per second, which means the amount of time per symbol is 1 millisecond. Alright. For every 1 millisecond I am transmitting a different symbol. Hence, in 1 second I am transmitting 1000 symbols, that gives me 1 kilobit per second. Now, if time is 1 millisecond, we know that the frequency bandwidth is 1 over time. So, the bandwidth required to transmit this signal, the bandwidth required for transmission is nothing but 1 over t, which is 1 over 1 millisecond, which is 1 kilohertz. So, roughly speaking, if I have to transmit symbols at the rate 1 kilobit per second or 1 kilo symbol per second, I need a time of 1 millisecond per symbol, which means I need a bandwidth of the channel which is 1 kilohertz. Alright. Okay. So, that is what we have without CDMA. Now, with CDMA, what I am doing is I am taking A0 and multiplying this with its code 111. Hence, I am transmitting A0, 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 A0. That is, I am transmitting each symbol. No, look at it, previously I was only transmitting one A0. Now, because I am multiplying with code, I am taking each A0 and I am multiplying with the code of length 4. Hence, it is giving me 4 symbols. So, each symbol A0 has now split into 4 symbols. In fact, if I use a code of larger length, it will be split into even larger number of symbols. So, I am taking this symbols and I am making many symbols out of this symbol. So, instead of transmitting one A0, I am transmitting 4 A0. Similarly, for A1, instead of transmitting A1, I am multiplying it with its code, which is 1, minus 1, minus 1, 1. So, I am transmitting A1, minus A1, minus A1, A1, which is again I am transmitting a sequence of 4 symbols. So, every symbol is being split into a sequence of 4 symbols. Now, to keep the symbol, remember earlier symbol time was 1 millisecond. Remember, the symbol time earlier was 1 millisecond. Now, each symbol has split into 4 symbols. So, to keep the symbol time constant, I have to transmit each of these symbols or each of these symbols after multiplying with the code in 1/4 of that millisecond. So, now the time that I need is 1 millisecond over 4, because now each symbol is splitting into 4 symbols. If I want to keep the symbol rate and the symbol time, if I want to keep the symbol rate at 1 kilobits per second, I need to transmit each of these sub symbols. In fact, these sub symbols have a name. These are known as chips. Each symbol is split into 4 chips. If I want to keep my symbol rate constant, I have to transmit each chip in a time that is 1 millisecond over 4, that is known as the time of the chip. Alright, I have to reduce the time of the chip, because otherwise if I multiply by a sequence that is 1000 chips long, then it will simply take too much time to transmit all the chips if I do not transmit each chip in a smaller amount of time. So, here I am keeping the effective symbol rate constant and I am transmitting each chip in a smaller time, and that time is 1 millisecond over 4, which is 0.25 millisecond. Hence, the bandwidth that is required now is nothing but 1 over T c, which is equal to 1 over 0.25 millisecond, which is 4 kilohertz. That is the trade off. Look at this. Previously, we needed a bandwidth of 1 kilohertz to transmit symbol rate at 1 kilobits per second. We are still transmitting symbols at 1 kilobit per second. However, now because we are multiplying with the code, that is increasing the bandwidth. We need a bandwidth that is now larger, that is 4 kilohertz. So, if I look at this system, at how this system looks, that system looks as follows. Previously, I had a signal of bandwidth 1 kilohertz corresponding to 1 kilobits per second. Now, I am taking this and multiplying this with the chipping sequence, alright, which is the code, which is 1, 1, 1, 1 or 1 minus 1 minus 1 1 and so on and so forth. That has resulted in increasing the bandwidth from 1 kilohertz to 4 kilohertz. Now, I have a bandwidth which is much larger, which is 4 kilohertz. So, remember, this is after multiplying with code. Alright, so before I multiply with my code, the bandwidth required is 1 kilohertz. After I have multiplied with the code, the bandwidth has increased to 4 kilohertz. Hence, the multiplying with the code has spread the bandwidth of the signal. Hence, this is the key word. Hence, multiplication with code has spread. Remember, the original bandwidth is small. Now, after multiplication, the bandwidth has spread. So, multiplication with the code has resulted in spreading or has spread the bandwidth of, or has spread the spectrum of the original signal. Hence, this CDMA is also known as a spread spectrum technology. That is why CDMA is also known as a spread spectrum. This is also known as a spread spectrum technology. CDMA is known as a spread spectrum technology, and this code which results in spreading the bandwidth is also known as, the code which spreads the bandwidth is also known as code C0, comma C1 which spread the bandwidth are also known as spreading. These are also hence known as spreading codes. Code C0, C1 as we have seen, they result in spreading the bandwidth of the signal, hence these are also known as spreading code. And finally, one factor that you can assume is the bandwidth increases or bandwidth spreads. Spreads by a factor of 4 equals n, which is the length of the spreading sequence, which is the length of the spreading sequence. So, the bandwidth spreads by a factor of n, which is the length. Remember, we use spreading a code of length 4, which is 1, 1, 1, 1 or 1, minus 1, minus 1, 1, both of them are of length 4, and we are saying that the bandwidth increases by a factor of the length of the sequence, which is 4. Hence, n is also known as spreading. The length of the code is also known as the spreading factor, or it is also known as the spreading factor. In the future, we will also see that it is also known as the spreading gain, because it results in noise suppression. However, we are going to see that as we continue with this lecture. N is also known as the spreading gain. All right. So, this is important. This terminology is important to keep in mind, that it is also known as the spreading gain. Now, let us look at other such spreading codes of length n equals 4. We have looked at two codes. One is C0, which is 1, 1, 1, 1. We have also looked at C1, which is 1, minus 1, minus 1, 1. There are two other such spreading codes. One is C2, which is 1, minus 1, 1, minus 1, and C3, which is 1, 1, minus 1, minus 1. So, these are a set of 4 codes. So, these are 4 codes or 4 spreading codes. These are codes or set of 4 codes, and further we also said the key property that these codes should have is nothing but orthogonality. We said these codes, to resolve the signals of each user, that is each of these users, we need these codes to be orthogonal. Hence, these codes you can see are not only ordinary codes, but these are orthogonal spreading codes. You can take any of these two codes, compute the dot product, and you can see that they are orthogonal. For instance, I will take two codes which are C2, that is 1, minus 1, 1, minus 1, and C1, which is 1, minus 1, minus 1, 1. So, let me take the two codes 1, minus 1, 1, minus 1, which is C2, and I will take it dot product with C1, which we had earlier, which is 1, minus 1, minus 1, 1. I will compute the dot product, and you can see that these codes, for instance, if I compute the dot product, this is 1 into 1, that gives me 1, plus minus 1 into minus 1, that gives me 1, plus 1 into minus 1, that gives me minus 1, plus minus 1 into 1, that gives me minus 1. So, I get sum 1 plus 1 which is 2, minus 1 which is 1, minus 1 which is 0. Hence, any two codes in C0, C1, C2, C3 are orthogonal. Hence, I can use C0, C1, C2, C3 to transmit 4 streams of information to 4 users, user 0, user 1, user 2, user 3. So, the number of users that can multiplex this common channel is nothing but the number of orthogonal codes, and we have seen that the number of orthogonal codes corresponding to length 4 is nothing but 4. So, let me write that down here. Number of orthogonal codes corresponding to length n is n. So, the number of, so if I given a code length of n, the number of orthogonal codes that exist are nothing but n. Hence, I can multiplex n users, because I can multiplex, I can transmit one information stream per code. I can transmit, given n orthogonal codes, I can transmit n streams of information. Hence, number of users that can access the channel simultaneously, that can access the common channel which implies, so the number of users that can access the channel, this common channel, is n. In this case, if n is 4, I can support 4 users. If n is 16, I can support 16 users. If n is, let us say 1024, that is 2 to the power 10, I can support 1024 users. So, if I want to support more users over the same channel, all I have to do is I have to increase the code length. So, that is the key. So, CDMA can adaptively support increasing number of users on the wireless channel by increasing the code length, so that you can have more and more orthogonal codes to support more and more users. All right. Now, let us look at another important concept. Let us look at a typical code. A typical code, for instance, C2 looks like 1 minus 1 1 minus 1. This, if you look at it closely, if I did not tell you that this was a spreading code, you would look at this code and you would see that this roughly looks like a random sequence of 1s and minus 1s. So, this looks roughly looks, that is the key, this is colloquial. So, let us not it has no technical meaning right now. It looks and it feels approximately like a random sequence of plus 1 comma minus 1. In fact, there is nothing random about this. This is a perfectly deterministic code. We know the code a priori. Hence, the randomness here is pseudo random. So, this is known as a pseudo random sequence. This is also known as, look at this, this also looks like some noise sequence. Hence, this is also known as a pseudo noise or PN sequence. Such a random looking sequence of 1 minus 1 1 minus 1, even though it is random, it is not exactly random, even though it is noise, it is not exactly noise, hence it is known as pseudo noise, or it is known in other words as a PN sequence. All right. So, this such code is also known as PN sequence. One technique to generate PN sequences of longer length, remember we need codes with longer length to support a large number of users. One technique to generate such codes of longer length is through what is known as linear feedback shift register. So, let me write that down. One technique to generate codes of longer length is through what is known as a linear feedback shift registers. All right. So this is also abbreviated as LFSR, where L stands for linear, F stands for feedback, S stands for shift, and R for register. So one technique to generate such sequences is through linear feedback shift registers. Let us look in more detail at the structure of a linear feedback shift register. As the name implies, I will first start with a sequence of registers. So let me consider a sequence of 4 shift registers. Registers are nothing but delay elements. So I will start with a sequence of 4 delay elements. Let me input here xi. So I am looking at the architecture of an LFSR, which is a linear feedback shift register. I am considering a sequence of 4 registers. I am starting with xi. I am inputting xi to the first register. Now at the output, since the register is a delay, I will have xi minus 1, that is the output of this register. At the input I have xi, at the output I have xi minus 1. Similarly, after one more delay, I will have here xi minus 2. At the third register, I will have xi minus 3. At the fourth register, I will have xi minus 4. Now I am going, so I have a linear feedback shift registers. I have a set of shift registers. Here I have a set of 4 registers. Input is xi, the output is first register is xi minus 1, second is xi minus 2, because register is after all a delay, third one is xi minus 3, fourth is xi minus 4. Now what I am going to, these are also a chain of registers. Now what I am going to do is I am going to do something interesting. I am going to take these xi minus 3 and xi minus 4 and I am going to combine them linearly. All right, what am I doing? I am taking xi minus 3 and xi minus 4 and I am going to combine them linearly, and not only that, I am going to feed this back to xi. So now let us look at the different components. I have shift registers. I am linearly combining. So this is the linear combiner, and the critical part is this, which is the feedback. This is the feedback part. I have shift registers, linear combining, and then I am feeding back. Hence, these are known as linear feedback shift register, and also abbreviated as LFSR. And this particular LFSR operates on the feedback equation, that is xi is xi minus 3 combined with xi minus 4. However, this combining is a binary combining, that is known as the binary addition in the field 2, or it is also known as the XOR operation. So let me clearly illustrate this operation. Xi is equal to xi minus 3 combined or XOR with xi minus 4. So the key equation, that is the key equation in this linear feedback shift register architecture that is illustrated here, is the feedback path, the combining in the feedback path, and we are saying that is generated as xi is xi minus 3 linearly combined or combined with xi minus 4. So, the equation of the feedback register is xi equals xi minus 3 XOR with xi minus 4. Let me remind you about XOR operation. XOR operation is nothing but if I have 4 elements 0 and 0, 0 XOR 0 equals 0, 0 XOR 1 equals 1, 1 XOR 0 equals 1 and 1 XOR 1 equals 0. Alright. So, if both xi minus 3 and xi minus 4 or both inputs to the XOR are either 0 or 1, then the output is 0. If they are both, if one of them is 0 and the other is 1, that is I have 0 and 1 or 1 and 0, then the output is 1. So, this thing is something like a parity. If it has even parity, then the output is 0. If it has odd parity, then the output is a 1. So, this XOR is something like a parity operation. Now, let us look at the operation of the linear feedback shift register implementing this feedback equation. Let me write down a table here. Here I will start with a table that is xi minus 1, xi minus 2, xi minus 3. Before I start that, let me also illustrate. Let me denote this xi minus 4 as the output. That is, not only am I feeding back xi minus 4 plus xi minus 3, I am also tapping xi minus 4 as the output. So, this is the output. Alright. So, I have xi minus 2, xi minus 1, xi minus 2, xi minus 3, xi minus 4. Now, for the sake of clarity, and using these I am generating the xi's at every instant. Okay. So, I have xi minus 1, xi minus 2, xi minus 3, xi minus 4, and using this I am generating xi at every moment. Remember, xi is given as a combination of xi minus 3, xi minus 4. So, if I know xi minus 3 and xi minus 4, I can generate xi as xi minus 3 XOR with xi minus 4. Hence, this xi minus 1, xi minus 2, xi minus 3, xi minus 4 is like a state of this register. Because if I know the state in which my feedback shift LFSR in, I can generate the next input which is xi. And remember, this is what is being fed back as the input. So, in the next instant, this xi will be fed back into the register. So, if I note the state, I can generate the output, and then I can also generate xi, and which determines the next state. Hence, this is a self sustaining loop. Alright, we will start the next lecture at this point, and we will discuss further the operation of this linear feedback shift register. With this, let me end this lecture. We will start the next lecture again with a discussion of the linear feedback shift register operation. Thank you.